We are going over test 1 review, which is here. Make sure you understand the homework and you can use this review as extra. Let's begin with number 1. We're asked questions about sets A, B, and C. First of all, let's write out A is just the set containing 1 and B is the power set of A. So B has 2 elements, the empty set and the set containing 1. And then we can also write down C. C is A union B. And so this is the set C. Now, let's answer these questions. First of all, is 1 an element of A? Absolutely it is. We see 1 here. It's listed as an element of A. Next, is 1 an element of B? No, it is not. Because you see, the set containing 1 is an element of B, but 1 itself is not. Now, what about set C? We have 2 questions. First of all, is the set containing 1 an element of C? Yes, it is. We see it listed right here. It is an element. So this is true. And now the other one, is the set containing 1 a subset of C? This also is true, but for a different reason. It's true because if you look here, this is the same thing as saying 1 is an element of C, and we see it right here, okay? So C, little c, and little d are both true. Now let's move on. We want to find 3 sets, A, B, and C, such that the intersection of all 3 is empty, but if you take any 2 pairs, they intersect, okay, with something in them. So what I can do is just start putting things here in a Venn diagram. And I had some other options here, but this is all I really need. Now let's write down the sets. A is the set 1 and 2. B is the set 1 and 3. And C is the set 2 and 3. And then, well, we can notice some things. If we take A intersect B, you can either look at the Venn diagram or look at the sets as listed. We get the set 1. If you take B intersect C, we get the set containing 3. And if you take A intersect C, we get 2. So you see, none of A intersect B, A intersect C, and B intersect C are empty. However, if we intersect all 3, we in fact do get the empty set. So this is a wonderful example. There are many others, in fact, infinitely many others here. Now for number 3, we are given a set A with 3 elements, A, B, and Q. And first of all, let's find the power set of A. Well, we know this will have 8, which is 2 to the 3 elements. And I will list them in order of cardinality. We have the empty set. We have the singletons. We have the sets with 2 elements. Cardinality 2, this would be A and B, A and Q, and then B and Q. And then there's only one subset of capital A with 3 elements. It's all of A. This would be A, B, and Q. This is the power set of A. Now let's move on here. We want the cardinality of the power set of this set here. So this set, and you can count to make sure, we have 8 things. So its power set has 2 to the 8 elements. So this answer is 2 to the 8. Now finally, we do C. We are computing a set difference here. So when we have a set difference, as we will also get to practice one down here, but we take and start with the elements of A and we remove the elements that are here. Well, if you look at A, which is what we're starting with, the only element to remove is this little b. So this set difference is little a and q. This set has 2 elements. Okay, that was number 3. And now, as I was saying, well, let's move on to number 4. Part A, this is a set difference as well. But look, right here, which I am shading, this is B intersects C. And then this part is A. So what I will shade is A, then remove this B intersects C. Let's outline it first. It would look like this. Here, now we color this in. We get all of this. This is A minus B intersects C. Now part B, we want A union B, which I've outlined in red, but then intersect C complement. So C complement, I will do with these lines. It's everything that is not in C. Okay, so now you take what's outlined or circled in red, intersected with these red lines, and again, let's outline it first. It will be precisely this. All in here is A union B and then intersect C complement. And this is the end of number 4. Now, 5 and 6, these are both truth tables, and I went ahead and got a jump start by writing all the columns. But let's talk about what we need to do. First of all, we have this, which is P or Q, if and only if, not P. And we want to determine whether this is a tautology, meaning always true, contradiction, meaning always false, or neither. And we will know when we get here. If we see a column of all T's, tautology. If we see a column of all F's, contradiction. And if we see anything else, it's neither. We have 2 input variables. This makes 4 rows in our truth table. P can be true or false. And similarly, Q can be true or false. Then we have an OR. And the only time an OR is false is one place. It's right here, when both P and Q are false. And the OR is true every other time. Now we have not P. So we just switch all the truth values from statement P. Now finally, we have this column, and we have an if and only if. The if and only if is true. Well, it would be when this column and this column have the same truth, meaning they're both true or they're both false. But the columns are never simultaneously false. So the if and only if is true here, and it's false here, and false here. So now ask yourself, is this a tautology, contradiction, or neither? This is neither, because, well, we see 3 F's and 1 T. Next, we want to determine whether this compound statement, P implies Q, and not P implies Q, is logically equivalent to Q. And we will do this with the truth table. Again, I have already listed the columns, and we have 2 possible truth values for P, 2 possible truth values for Q, and this makes 4 rows in our truth table. Now, first we have a P implies Q, and the only time this is false is here, when you have a T followed by an F, and the implication is true every other time. It's true in these rows. Now we have not P, where we just flip all of the truth values for statement P. Now, we have another implication, but this time it's not P implies Q. And you see, we're looking for a T followed by an F. And that happens here, a T followed by an F. So this is false here, but in the other 3 rows, you see we have T followed by T or F followed by anything. The implication is true. Finally, the last step is we have an and. We take this column and we perform and, which the and is true only when both are true. This happens, we see, in row 1 and row 3. Now, what are we trying to compare here? Well, we want to determine whether Q, which is this column, is logically equivalent to this statement. What do we see? In both we see TF, TF. The answer is yes. As columns 2 and 6 have the same truth values, and this is for all possible inputs, well, we see that this expression, P implies Q, and not P implies Q, that this is logically equivalent to Q. And this is the end. Okay, we have justified. Very nice. Now let's move on. This is a really great exercise, number 7. So P of xy is some statement about 2 integers. And then we know, or we are assuming, that this is true right here. For all x, there exists y, P of xy is true. Which other of these must be true? For all x, there exists y, not P of xy. Well, that's not guaranteed by what we're assuming. But the others, well, I will just say we can say yes, but let's talk about why. This one might be a little easier to see immediately. If it is the case that for all x, there exists y, P of xy, certainly there exists x, there exists y, P of xy, because we had a for all, and so we can definitely conclude there exists. Now, what about this other one? Oh, so let me outline. This one, yes, that is one answer. But let's talk about this middle one. This statement, there exists x for all y, not P of xy. Well, how do you negate quantifiers? Well, as we move a negation inside, it switches the quantifier. So this would be equal to for all x, not for all y, here. And then we can move the not in one more time. This would be for all x, there exists y. Now, we would have not, a not, and this is just P of xy. From our work, you see this statement right here is logically equivalent to this one. Okay? And so, of course, if this is true, so is this. And this is the end of number 7. Now for number 8, we have 2 statements to negate. First, we need to negate an and. Let's remind ourselves of De Morgan's. It says if we have P and Q and we want to negate, this is not P or not Q. And we will use that here. Well, in this example, this is my P, this is my Q. So when I negate, well, this would be, it is not Monday, or it is snowing. Letter B, we want to negate for all x and z, there exists y and z such that xy is a natural number. Well, you see, it's very similar to this up here. where we will bring the not inside, and as we do, we flip the quantifier. In fact, you see we have a for all there exists, and when we negate, you can see what will happen. We will have a there exists followed by for all. So maybe I will just write that. This will be there exists x and z, okay? And then this will be a for all y and z. Now we negate this part. X, y is not a natural number. Just as a comment before we move on to the next example. This statement is true. Just take x equals 0. X equals 0 is an integer, and no matter your integer, 0 times that is 0, which is not a natural number. Similarly, this statement is false, as it would need to be because its negation is true. In particular, for x equals 0, this doesn't work. Okay, that was just a comment. My final answer is here and here. Now for number 9. We are counting. This is fun. We start off here. We have 8 letters. And we're interested in making 7-element strings using these 8 letters. Well, these are lists of length 7. So we start with part A. We have no restrictions. We can repeat, and we're just trying to use the 8 letters. So here we have 8 possible letters we can put in the first spot, 8 possible letters for the second, 8 for the third, 8 for the fourth, all the way out to 8 possibilities for the 7th. And you see, multiplication rule gives us a total of 8 to the 7. This is letter A. Now we have to think a little bit more for B through E because we have some restrictions here. For B, we want to begin with R and end with T. So we have one possibility here. It must be an R. We have one possibility here. It must be a T. But then we can put any of the 8 letters in the other 5 places. Altogether, we get 8 to the 5 power. Now for C, begin with A or W. Well, this says we have 2 choices for the first spot. This is either A or W. Then we have 8 possibilities for the other 6 entries of my list. Altogether, you see I have 2 times 8 to the 6. Now for D, exactly 4 Z's. Well, let me do this as a 2-step process. Now, I will not choose all possibilities, but let me show you one choice of 4 Z's. Maybe this is Z, this is Z, this is Z, and this is Z. Okay, there's one choice. Now, for instance, I can put a Z in each one of these. Okay, that was one choice. Well, how many choices were there? Well, we have 7 entries, and we want to choose the 4 locations for the Z. Now, once we have done that, and like I said, I illustrated one, but there are 7 choose 4 possible ways I could have selected those 4. Well, we have 7 more letters because we cannot use Z again. So I have 7 possible things here, 7 here, and 7 here. So this would be times 7 cubed. This is D. And finally, for E, 7 distinct letters. We cannot repeat in this example. So we have 8 possible choices for the first entry, 7 possible choices for the second, then 6, then 5, then 4, then 3, then 2. Because, for example, once I've chosen these 3, for this spot, I can put anything of the 8 letters except the 3 I've already chosen, and that would be 5, for instance. This we know, we were calling this P87. You can also look at the formula and notice that this is just 8 factorial. Either one of these is perfectly fine. Now for 2 questions that involve the binomial theorem. Here we have number 10 and 11. The first thing with number 10, we see a 9 to a power minus 1 to a power, and 9 plus minus 1 is 8. Wonderful. So we let x equal minus 1 and y equal 9 in the binomial theorem. Then, well, 8 to the n. This is definitely minus 1 plus 9 to the n. Then we expand using the binomial theorem. This would be a sum. K goes from 0 to n of n choose k, minus 1 to the k, 9 to the n minus k. And all I need to do to finish justifying this combinatorial identity is just rearrange. This is a sum, k equals 0 to n. I can write minus 1 to the k on this side, and then I have n choose k and 9 to the n minus k. This is exactly what we wanted to show. This is the end of number 10. Now for 11, okay, like I said, this again is binomial theorem. We know 2 minus x to the 7th power. This is going to be a sum. K runs from 0 to 7 of 7 choose k. We have 2 to the k, and then minus x to the 7 minus k. Now, we want the coefficient of x to the 5th power. So we want the following, that 7 minus k is 5, and this means that k is 2. When we do this, we get the coefficient is 7 choose 2, 2 squared, and then minus 1 to the 5, which is negative 4 times 7 choose 2. This is my coefficient. Now, what is 7 choose 2? Well, you can either use the formula. It would be 7 factorial over 2 factorial times 5 factorial. But another fun way to see it is here. You see, this is the Pascal's triangle. And here's the row for 7 choose, say, k. And 7 choose 2 would be here. So you see, 7 choose 2 is 21. My final answer here is minus 84. We have one more problem, combinatorial proof. I need to create some story, counting story, say, that both the left-hand side and the right-hand side count. Now, we see a product of 2 binomial coefficients. So you could think subsets and create a story. I think what I will do is create a story about a group of students. But there is no order in my story, right? Because we know, for example, n choose r is the number of r element subsets of a set of size n, or equivalently, the number of ways to choose r elements from n. There is no order here. Okay, well, suppose we have n students in a class. Well, what I would like to do, we want our students to work on a project and K of the R students to present the project. Say to the class. This will be my story. What I need to do is argue why this side counts the number of ways to do this, the number of ways to choose our students and K of the R to present, and also why this counts the number of ways to do this. We may count, just like I said, the number of ways to select R students from the class of N and then K students from the group of R as follows. And I will give two different options. So option 1, this will be the left-hand side. Well, first, select R of N students for the project. Then K of the R students to present. How many ways to do this are there? Well, this is multiplication rule. First, out of N, we choose R, and then out of R, we choose K ways. This is option 1. Now for option 2. Well, if you look at the right-hand side, this says, first you choose the K students to be presenters. And then, well, you see we need R minus K more students to make up the group working on the project. So out of the remaining N minus K students, we fill out the rest of the group by choosing R minus K. Well, that's the idea. Let's just write this down. So first, we select the K of N students to be presenters. Then, out of the remaining N minus K students, we want to select the R minus K to fill the group of our students for the project. Once again, we use multiplication rule and we see there are, well, first you choose K, and then out of the remaining N minus K, we choose the remaining R minus K people to work on the project ways. So altogether, you see we have option 1, option 2, they're both counting the exact same thing. And so we have justified that this combinatorial identity holds. The left-hand side and the right-hand side are in fact equal. And this completes the end of this combinatorial proof. It also completes the end of test 1 review. Thank you all so much.